Consider a mass-spring-dashpot system. Here I have one example of such a system. Here's bike example. This system mass is, say, the person on the bike and the bike itself. The spring you can see is there. And for the dashpot, you can think of the shock absorber. So that one will help the bike. Without this, the bike would continue to bounce up and down after hitting a pothole. Yeah. So that is one example of such a system. In this example, they give us the mass m equal to 1, k is a spring constant, it is the stiffness of the spring, and c equal to 0. In this case, the damping coefficient is 0. This system is governed by the differential equation f x double prime plus c x prime plus kx equal to ft. Here ft is an external forcing function. And they also give us these initial conditions: x0 equals 0, x prime 0 equal to 0. This ft, the external forcing function, is a piecewise continuous function. So we can rewrite that with just one formula using the unit step function. To solve for xt, we just need to Laplace transform both sides. Yeah. So here's how we do it. I first write down ft as just one formula to apply the Laplace transform of the function involving unit step function ft. So we have the signal psi of t starting from the time 0, so it's psi of t. And now, starting from the time 2 pi, we want to cancel this signal out. So this is starting from ut minus 2 pi, starting from 2 pi. You want to cancel that signal. So this is minus psi of t. So ft psi of t minus ut minus 2 pi psi of t. Yeah. We can use this function that will help us to Laplace transform both sides of this equation. Now plug in all the data they give us. M equal to 1, so you have x double prime, c equal to 0, so 0 x prime, k equal to 4, x equal to f of t, equal to this function. Laplace transform both sides, you have Laplace transform of the left hand side equal to the Laplace transform of the right hand side. Laplace transform x double prime. So in this case, so easy for us because the initial condition, this one and this one are both 0. So in this case, Laplace transform x double prime give us s squared big X. So here's big X I use for Laplace transform of small x. In general, we have Laplace transform of x double prime equal to s squared times big X minus s times small x at 0 minus x prime at 0. However, in this case, both x0 and x prime at 0 are 0, and therefore I only have this term s squared times x plus 4 times Laplace transform small x, so 4 times big X, Laplace transform of psi of t equal to 1 over s squared plus 1 squared. Laplace transform of these terms, let me write out the formula separately. Laplace transform of the function u t minus a f t minus a, you can find that in the Laplace transform table. You have e minus a times s, big F of s. So in this case, you see here t minus 2 pi, a equal to 2 pi. So we try to get the form t minus a for the psi of t. So we want to compute Laplace transform of this one. We want to compute Laplace transform of this function. We know that a is 2 pi. Now we want to write f t minus a, or psi t minus a here. We know that psi of x or psi of t here is a periodic function. It has a 2 pi period, so you know that psi of x equal to psi of t minus 2 pi. U t minus 2 pi times psi t minus 2 pi. This is true because psi of t equal to psi of t minus 2 pi. And now we can use the formula up here. We have e minus a s is minus 2 pi times s times Laplace transform of psi of t. Remember that f of s here is the Laplace transform of small f of t. So you have Laplace transform of psi t. Based on this formula, we have this one. Now this one gives us e to the minus 2 pi s times 1 over s squared plus 1 squared. And with that, this one equal to the first term minus the second term. So here is what we have after Laplace transform both sides. The left hand side is s squared plus 4 times big X. The right hand side is this term. Divided both sides by s squared plus 4, you have big S. 1 over s squared plus 4 times the right hand side. So we have 1 over s squared plus 1 times s squared plus 4 minus e minus 2 pi s 1 over s squared plus 1 times s squared plus 4. You can just inverse transform both sides. You can find the function small xt. So small xt is the inverse transform of the right hand side. So inverse transform of this one minus the inverse transform of the second one. For the first term, I will just use partial fractions decomposition. So let's do the first term. For the second term, this and this one is exactly the same. You have e power minus pi 2 pi x. This one you use the formula we have tried before. We use this here. Actually, this is a translation on the t-axis. So e to the minus as, e to the minus as times this function. The inverse transform this one is this one, ut minus a, ft minus a. So we can find this one, the inverse transform this one, and we apply this formula. So let's compute the partial fraction decomposition for the first term. This one equal to, we know that it should be a constant times, this should be s squared plus 1, s squared plus 4 here. So this one, you can put s squared plus 4 minus s squared plus 1 here. You get 4 minus 1 is 3. So 1/3 is outside. Inside you can just put 1, 1. That's how I find that number without needing to compute the constant A, B, C, D. Inverse transform both sides of that. We have inverse transform of left hand side, which is actually the first term here, equal to 1/3 inverse transform of 1 over s squared plus 1 squared minus inverse transform 1 over s squared plus 2 squared. Here's 1 square. So in order to have 2 square, fit 2 square here, I want to have 2 here and 1/2. Put 2 here and then divide by 2 out there. Now this one, we know that sine of kt or sine of t in this case send to Laplace transform sine of t is 1 over s squared plus 1 squared. Same here, sine of 2t. Laplace transform that's 2 over s squared plus 2 squared. And therefore this one is 1/3 sine of t minus 1/2 sine of 2t. So this is the inverse transform of this one, which gives us the first term. The second term, we use a translation on the t-axis. We use the formula of the translation on the t-axis, this one. So in this case, you see that we can apply for big F of s in this function. E minus as is minus 2 pi s. A equal to 2 pi. E minus 2 pi s times big F of s. E minus 2 pi s times big F of s. The function transform to this one is u t minus a, t minus 2 pi. Small f t minus a. Small f of t is this function. Here is our function, small f of t. We want t minus a. So the place we see t, we put t minus a there. T and t minus a. T minus a. T minus a. So this is the inverse transform of this function. Here I need to remember a equal to 2 pi. A equal to 2 pi. So we can write as u t minus 2 pi times 1/3 sine t minus 2 pi minus 1/2 sine 2t minus 2 pi. And because sine of t minus 2 pi equal to sine of t, sine of 2t minus 4 pi equal to sine of 2t. So that's equal to 1/3 u t minus 2 pi times sine of t minus 1/2 sine of 2t. That one is the inverse transform of the second term. Inverse transform of the second term equal to this function. So we computed the second term. Now all together we have xt here. We have xt equal to the first term minus the second term equal to this term minus this term. So we see that we have 1/3 sine of t minus 1/2 sine of 2t in common. So let me write as 1/3 sine of t minus 1/2 sine of 2t multiplies 1 minus ut minus 2 pi. This is our answer for the solution xt.